Hello, everyone. I'm Akanksha Kapil. I am the Content Marketing Manager with Delta Q Technologies, part of the Zappi Group of companies. I'd like to welcome you to today's panel discussion. Please remember that this session is also being recorded and will be available to watch on demand following this session. If you have any questions for our panelists during the session, please add them to the Q&A tab, which you can find at the tab to the right of your screen. Note that your questions will be sent privately. With that, I would like to introduce you to our speakers today. I'd like to welcome Conway Hui from Delta Q Technologies, who's our a panel discussion moderator, and then our panelists, Chris Botting from Delta Q Technologies, Luca Vezzadini from Zivan, and Erik Stafl from Stafl Systems. I will now pass it off to Conway. Please take it away.
Okay, thanks, Katja. Yeah, I'll be moderating this discussion today on the future of battery and charging technology. I'm the Director of Sales Application Engineering and Customer Support at Delta Q. I've been in this industry for over 16 years now and have seen it come a long way. But with me today are some very knowledgeable, much more knowledgeable than me people, and we'll go around the screen here and introduce everyone. So Chris, why don't you go first?
Thanks, Conway. I'm Chris Botting. I manage research at Delta Q Technologies. I've been in the commercial EV industry for over 2 decades in one shape or another. What I do at Delta Q is I manage internal engineering development and research collaborations with university partners on power electronics to make our chargers smaller and more energy efficient, and also run our battery testing lab where we look at life of batteries and charge profiles and energy efficiency.
Okay, let's go to Luca next, please.
Okay. Good morning to everyone. My name is Luca Vezzadini, and currently I hold the position as an application engineering here in Zivan, so a division of Zappi Group. So since I joined to the company, my role is to support the electrification for no-road mobile machinery and all-road vehicle application. Before moving to Zivan, I work as an embedded system engineering in another company who is specialized in delivering a solution for non-road mobile machinery.
Okay, thanks, Luca. And our special guest, Erik Stafl.
Hey, good morning, everybody. My name is Erik Stafl. I'm originally an MIT graduate, a degree in electrical engineering, computer science, and a focus on power electronics. I've spent the rest of my career since then working on battery management systems and battery pack development. So through Stafl Systems, I've had the privilege to work on something like 50 different battery programs, all using lithium-ion, NMC, LCO, LFP, and LTO chemistries, and really seen how deep the topic of battery management systems and understanding proper functioning of battery pack goes. So really happy to be here and looking forward to the discussion.
Okay, thanks everyone, and thanks for being part of this panel. Let's get right into the first question that's probably on everybody's minds, seeing the title "Future of Battery and Charging Technology." Is I've seen the industry and really the world go from not knowing what lithium is and just nickel or lead acid to pretty much people having multiple lithium packs in their lives, be it in phones or computers, in their cars. But what's next? Where is lithium going? Who wants to go first?
Well, I'm happy to take a quick stab at that.
Sure.
So it's funny. It's batteries have gone from a topic of kind of deep, research and only experts know about it to now, if you're at any party or anything and someone hears you're in batteries, they all have a story or question, and they say, "How do I take care of my batteries?" So you're absolutely right, Conway. As far as societal implications, everyone's using them and everyone understands the importance of lithium-ion. Now, I get this question a lot, which is, what's going to replace lithium-ion? What's going to be the next thing? And what I like to say is there's a reason lithium is the battery chemistry of choice. And the reason why is looking at the periodic table. If you look at it, it's upper left, element number 3. So it's very lightweight and highly electronegative. So that means it's a very ideal ion for this sort of chemistry for energy storage. That being said, there are a million different flavors of lithium ions. So that's the thing that we need to consider is, previously you'd have lithium cobalt oxide, which was a common kind of consumer grade, and high energy, but not necessarily the most cost effective lithium technology. But then longer lasting NMC cathodes have come out and other kind of improvements. So to my best guess, I would say over the next 10 years, we're still going to be talking about lithium. It's just going to be different variants of it, different flavors of it. So you may hear things like 811 lithium NMC and high nickel content, stuff like that. There's a variety of tunings that could still be happening at the cathode and the anode level that still mean that we can extend the capability of lithium ion, the core technology, quite a bit further. But it's a very broad umbrella, and I would caution anyone to not think that lithium ion is like one thing. It's a very, very broad spectrum of chemistries. But I'll pause there and let some of the other people speak about.
Luca or Chris?
Yeah. So it's very difficult to predict the future, but for sure we have a lot of, we can see some trends also in automotive sector. So what we can see in particular from Toyota and Dyson, that they are investing a lot in the solid state battery, so in which they are going to use the solid electrolytics instead the liquid one. So the advantage is everyone knows, so it's an higher density and improve safety. So we can reduce also how to reduce the charging time, so we have less prone to exploding. So there are some benefits, but yeah, we have also to think not only to the lithium battery, but also how to manage this battery. So we have also to consider that for the lithium battery, there could be also the heat. Another technology is the heat management, the heat management system. So we have also to take care that once we talk about the lithium ion, it's not only the problem of the new technology, but also how to manage this new technology. For example, for the heat management system, we have the PCM, so the phase change material. So it's a very huge word, and for example, this can be integrated in the lithium battery because they allow to facilitate the thermal management, changing the phase of the material that can be integrated into the lithium-ion batteries.
Yeah, I have to agree with those comments from both Luca and Erik. I think we shouldn't be thinking of lithium ion as one thing, or that it's binary, that it's going to be replaced by something else. I think we're seeing a continual evolution and a refining and improvement. I know we've seen a lot of battery technology come and go. Early in my career, I was doing hybrid buses and trucks. This was 20 years ago, and we were using AGM, so sealed lead acid batteries, and then moved it up to nickel metal hydride, and then moved on to lithium ion in the early days when it was very expensive, when it was around $1,000 per kilowatt hour at the pack level, and now we're down to $150 per kilowatt hour. Things have come down in a very significant way, and I think that that's really going to be the story. Not that things are going to move on to a new magic chemistry. You see press releases and articles all the time, but I think at this point it's really more of a commercialization story as the manufacturing scales up and the supply chain and the way the batteries are packed into modules and packed into packs and managed. As that matures and is optimized, things are growing at a scale where it's difficult to see any other chemistry coming in that requires totally different tooling and displacing it. Which isn't to say that there aren't new things. I mean, the voltages keep on being pushed up, and the performance and the charge rates. There's continual movement to use less, cobalt, which is costly and has issues with the ethical sourcing and so on. And so whether it's, lithium iron phosphate that has no cobalt, or moving to the 3 metal oxide blends that just use less and less cobalt, I think that's a clear trend. But I think at the end of the day, we're not going to see anything replace lithium ion in the next 10 years. We're going to see a continual refining and evolution, which would include, solid state batteries and things like that, which are going to continue on the lithium ion platform, I think.
Yeah. So it sounds like we're still going to be using the word lithium. It's just everything around it may be a little different. Now, I think Luca brings up an interesting point about heat management, or really temperature management of the packs. We're seeing a lot of fully temperature controlled packs in automotive and larger machines. Do any of you think this is going to translate into the smaller packs and some of the more industrial markets that we deal in? Erik's nodding his head.
The short answer is yes. Yes.
Yeah. And
the
how
reason I say
how
that
do you
is-
get it?
Yeah, the good question, because one of the things that's interesting is, as Chris was saying, lithium ion cells used to be very expensive on a per energy storage basis. So, north of $1,000 per kilowatt hour. Now, in high volume application, cells are, right around $100 a kilowatt hour, depending on exactly the flavor. So the cell is less and less a fraction of the value of the pack that it used to be. So I guess the point I'm trying to make is now there's going to be a focus on cost reduction of the other ancillary pack components that needs to be considered as well. So that's thermal management, that's mechanical structure, and BMS. Specifically as it pertains to thermal management, one of the things to note is your pack is typically only as good as the weakest cell group. And so what that means is that if you have a pack that's 80% excellently thermally managed, but you have these corners or some odd locations in the pack that are not cooled or heated properly, your pack's going to have reduced performance overall. So it's like a daisy chain phenomenon where you have to make sure every single link in the chain is strong. So for that reason, thermal management is absolutely critical from a performance and a safety perspective. But there are new technologies coming out each year about really innovative ways to do thermal management. Very efficient liquid cooling channels, immersion cooling sometimes is looked at as well. There's a variety of methods to try and improve the thermal management, even in more kind of industrial grade packs, not so much automotive. So I would expect the short answer, Conway, is absolutely. I think we're going to see a lot of investment and focus on the thermal management of lithium ion packs in basically all applications over the next few years.
Cool. Thanks, Erik. Now, Luca, you brought this up. What have you seen for heat management in lithium packs?
So from the two main way to cool the system are the air cooling or the liquid cooling. So you have the 50% of water and 50% of glycol, which is the standard used not only for the off-road mobile machinery but also to the automotive one. So what I also investigate in this period, so is the phase change material. This is a new heat management. So as I told you previously, is this kind of material which is able to change. So it has to store in the battery and change their phase. And once they change the phase, for example, from solid to liquid or to liquid to gas, is able to release the cool, so is able to reduce the temperature of the battery. So, and I think that this could be also a new technology that we can see in the future.
Does that phase change material, can that also heat the pack?
Yeah, I think yeah.
Okay, interesting. Chris, any thoughts on thermal management?
Sure. Yeah, I think the thermal management that makes sense is going to depend a lot on the application, both in terms of what the machine or the vehicle looks like, and in particular what the duty cycle, what the usage profile is. So clearly, managing temperature matters. We all know the from a chemistry point of view, for every there's the old rule of thumb that for every 7 to 10 degrees Celsius over 30 Celsius, you're looking at the shelf life or the calendar life of the batteries being cut in half. So if you've got batteries running at 50 Celsius, they're going to last half as long as they would if they're running at 40 Celsius. Now that's sort of averages or histograms of use over time, and the time at high temperature has a disproportionate impact. So things like phase change material, which is a passive cooling method, or really sort of storing the heat, and taking sort of a spiky temperature profile and smoothing it out. That can take some of those peaks out, and that can have a disproportionate impact on extending life of the cells and also helping them to stay better balanced. It also, of course, adds cost, size, and weight. So there's an impact on the density. But what's nice about passive methods like that is that it may be a fit for smaller machines where liquid cooling isn't really an option. Clearly in larger machines and larger vehicles where gas and diesel engines are being displaced, there may already be a liquid cooling system, and there's high duty cycles. There's an expectation of high power, long shifts, and particularly when there's high power DC fast charging, then there's a lot of heat which has to be managed. And on subsequent long cycles or multi-shift operation, that heat can keep building up and it just has to be taken out. And liquid cooling is the most effective way of doing that. But it's a significant complexity and cost to the system. So that'll make sense more if you already have an application where you need liquid cooling for your traction system. In a lot of smaller machines, fan cooling is still totally reasonable, and in some applications like smaller industrial machines, golf cars, forklifts, things like that, it's just passively cooled. And as long as the charge rates aren't too high, if it's being charged overnight or off shift with an onboard charger, then the duty cycle gives it time to cool. I think somewhere around a 1 hour charge rate, 2 hour charge rate would kind of be the point that I would say that you should be starting to look at active cooling of the battery, because that's the point where you're actually generating heat in the battery during the charge, rather than that being an opportunity for it to cool before the next use or the next shift.
But it's not just cooling, is it? It's also heating.
Yeah, one thing I was just going to add there, Conway, as you touched on it, is cooling is very important, but there's also heating. So particularly one of the things that's very critical for everyone here to understand is all lithium-ion battery chemistries really do not like to be charged at cold temperatures. It's just a fact, basically, because if you have a pack at, say, negative 10 degrees C, a lithium-ion chemistry, and you try and slam, especially a fast charge current into it, it's going to damage the cells very, very quickly due to lithium plating, because it just does not have the ionic mobility at those low temperatures. So it's very important to make sure that you also have mechanisms for heating, and those can be simple like film heaters or some sort of dissipative method, or it can be a fluid heater that then warms the fluid that actually is in thermal contact with the cells. So but it's very important to consider that early on, especially if you have a cold temperature application. So for example, if you're making a vehicle that's going to be used in the winter or in Alaska or Canada, in very cold temperatures, it's just very important to understand that there might be significant design features that need to be added for that, as well as changes to the operational regime. So for example, if a customer takes, an ATV, that's an off-road ATV in a negative 40 degrees C, temperature, and they plug it in, it's got to heat up for an hour or two before it can even start charging. So that's something that just needs to be considered for low temperature operation as well.
Thanks, Eric. I think you mentioned something that I want to touch on, and we're talking about the future of battery technology. I know we said everything's going to be lithium, but I think the next kind of buzzword might be solid state, which is actually still lithium, but it may take over the phrase in the industry. What's everybody's thoughts on solid state? Where's it going, and when we're going to have solid state batteries in our cell phones?
I think the first thing I would say about solid state is that similar to lithium ion, it's not a single thing. So it's a broad term. There are arguably a bunch of different kinds of solid state lithium ion batteries that are on the market now. It's just comes down to what that definition of solid state is. So there are some batteries out there that have a gelled electrolyte, which is semi-solid, which is not the same as having a ceramic or a glass, solid separator. But the overall goal with the solid state batteries really is to have a electrolyte which is non-flammable, and a separator which is permeable, such that lithium dendrites can't grow through it and cause soft shorts, which then become hard shorts over time. So it's dealing with that fire concern, and then as a bonus, you actually get to remove some of the active material on the anode side, and that can increase density, again, depending on which flavor of solid state that you're talking about. If you're starting to talk about actually moving toward the point where it can actually be a lithium metal battery. So I think we'll be talking about solid state. I think we'll be talking about lithium. It may no longer be lithium ion at some point, and I think there'll be as some of these technologies start to be commercialized, and some of them are being commercialized now. I think there'll be some education of what the different flavors are in that spectrum of battery technologies.
Erik or Luca, any thoughts on solid state as a future?
I'm agree with Chris. So I think that we will have two main street or two main paths for the future. So one is the still continue improvement or development for the lithium-ion battery. So we still to reduce the dimension and everything. And on the other side, I see that a lot of startup mainly start to provide a new technology. For example, I see also something on the hand. So, but I think, as Chris said, that the solid state will be the future, because at the end of the story, as engineer here, we have to trade off between the performance, cost, availability, and also this is just a topic that I hope to discuss in the future about the recycling. So we have to manage all these things together.
Now, one of the promises, or maybe this is just what I've read, but one of the promises of solid state is even faster charging rates. What kind of practical or kind of laws of physics limits are there to how fast you can charge a battery? Because you see a lot of promotions on get certain battery technology, you can charge your car in like 3-4 minutes or something like that. What's the practical limit here?
Yeah, fast charging is a really interesting topic, and obviously that's been really important with DC fast charging for electric vehicles, and I think consumers are starting to get experience with that. Really, it comes down to ionic mobility as well as internal resistance. And Conway, you mentioned what are the laws of physics or the physical limitations. What's interesting about battery technology is we're really not encountering the laws of physics. We're encountering weird glitches in chemistry, basically, and that's much less clear. And so there's no theoretical limit to how fast you can charge some sort of energy storage method. It's just a bunch of practical limits in terms of, well, this pack, this cell has a certain internal resistance at this temperature. We can only push this many ions over because otherwise it's going to get too electronegative and it'll start plating. So they're very practical limits, but each one of those can slowly get solved. So I like to say the battery industry is really a game of inches, and that's how you win the game. It's not like, I would say the press doesn't really do a good service by saying, how many times have we all read an article about, oh, in 3 years, the battery industry is going to be turned on its head. It didn't happen. What happens is we have 5 to 10% improvements year on year of a variety of different lithium-ion chemistries. And that over time, compounded like an investment, means that batteries today are much better than they were 10 years ago. But it's not because of some magic breakthrough. It's because of a number of very discrete and notable steps that basically get added up. So fast charging has basically been enabled through a variety of those. And I expect we'll see more and more of that. One thing I do want to say, though, is once you start getting to the extreme limit of fast charging, so say that you have a, 200 kilowatt hour battery for a high range electric vehicle, and you want to charge that in say 2 minutes, the amount of power you need for that is extreme. And so at that point, you actually run into other limits, which are at the grid level, because you can't just all of a sudden go from taking no load to dumping in 4 or 5 megawatts on a vehicle. That would dim the lights everywhere around. So that's really where we need to think about battery-backed DC fast charging. And then I would say at some point, the limitation is going to be that, not so much the chemistry itself. But I would say 5-minute charging around then is something that we will see, and we'll probably start standardizing around a lot of applications.
Yeah, if you have a little mini power plant right next to the charging station.
Yeah.
Exactly.
Yeah, I would echo that. So I think fast charging, well, for starters, the definition of fast charging really depends on the industry and the context that you're in. Looking at the golf industry, where Delta Q has operated for many years with golf cars, as they moved from lead acid to lithium, that's reduced. Well, in the forklift industry, traditionally, a 8-hour charge was a typical charge time for lead acid. So in 3-shift operation, in a 24/7 in a distribution center in a warehouse, you would you'd have 3 shifts and you'd have 3 batteries. So each battery is used for a shift for 8 hours, then charged for 8 hours, and then rests and cools for 8 hours. And in the past, fast charging meant being able to charge that battery at a 4-hour rate instead of an 8-hour rate, and that was still pushing what the chemistry could do, and it would still need some equalize and some longer, gentler charges, maybe on a weekly basis as maintenance. With lithium ion, it's no issue to charge at a 1-hour rate typically, and then going faster than that really comes down to the conduction losses, both in the cell and the pack and in the charge path from the charger. And then, as Erik alluded to, you start running into more practical limits with the grid connection that you have, and also, frankly, how much charger you're willing to pay for, how much copper you're willing to pay for and are able to lift. We're seeing liquid cooling in the in the automotive EV fast charging. They're liquid cooling the cables so that they don't have to have so much copper that it's not practical for a typical user to be able to actually lift and plug in. I think that's sort of getting at the practical and the economic considerations. So in golf cars, when they moved from lead acid to lithium, which is something that's been happening over the last 5 years or so, and it became possible to charge faster than 8 hours. What we're seeing is actually not necessarily fast charging as it would be defined in some other industries. One of the first things that was done was to reduce the size of the charger, because now that the battery was a bit smaller, because it didn't need to be oversized for capacity loss at end of life, and it could be charged at full power for the entire charge, it was now possible to charge in 4 hours instead of 8 hours, or just cut the battery power, cut the charger power in half, and reduce the cost of the charger. And in some cost-focused industries where you have a certain amount of time to charge, that may be what they choose to do with the added charge capability, rather than pushing the bleeding edge of what's possible. But I think there are limits to how much charger people are willing to pay for, and how much can be fit on board, or if it's off board, what that connection system looks like and how it plugs into the wall. And ultimately, it comes down to the physics of the size, the copper, and the heat removal, and the economics of the charger and the grid connection.
How about Luca? Luca, you have any thoughts on fast charging?
Yeah, I have some thoughts. As Chris and Erik said, the main disadvantages are, from the economic point of view, are the charging infrastructure, the cost of the charging infrastructure, and also the cost of electricity. So how much is the customer can pay for it? So we as a Zivan, we also produce the fast charging for our customer. Typically, the fast charging are off board, so we have a specific structure, specific charger, which provide to the customer a very quick charger. We are talking about around 30 minutes or 1 hour of charging. In particular, the fast charging for the off-board vehicle you are going to use during the lunch time or the break during the working time. So this is could be a limit to the cost, but also another issue from practical point of view could be also the availability of the structure of charging. So if we are, for example, if we are thinking about some place not close to the city, it's also difficult to provide to them the electricity necessary for the fast charging. Here, clearly, we are talking about the off-road vehicle, for example, an excavator. Clearly, if we are moving to the, for example, automotive, we have also to increase the availability of the power. So sometimes for the fast charging, we are also talking about 1,000 of kilowatt. So it depends application and also from the battery chemistry.
Well, personally, I was a little averse to fast charging at first because, and actually a lot of the material out there from the car manufacturers, and I keep quoting car manufacturers because that's what the general public or most people, even in our industry, will get their battery information from. And a lot of that material still says to fast charge if you need to, but not all the time. So at first I was a little adverse to it, but there's some data out there from the most early Model S's, which had all free supercharging at first, and so these cars were basically only supercharged and only fast charged, and their battery degradation was actually pretty reasonable, very low, in fact, like on the order of less than or 5 to 10% over a course of like 10 years or something. So that's actually very encouraging for fast charging as one data point. But speaking of more industry buzzwords, why don't we talk about wireless charging, which everybody wants to have. I have wireless charging on my phone. I have wireless charging on my toothbrush. When am I going to have wireless charging on everything else?
Yeah, I'm happy to talk to that one. We've done some work on wireless charging, not some work internally, and also with some of our university partners, doing research on it, because it's a technology that we want to keep sort of a watching brief on. But Delta Q doesn't have any wireless charging products today, and that's really because it's something that, although we get some questions and some interest, it's not currently something that looks like there would be a large business case for a significant number of our customers. And really what that comes down to is wireless charging has to add another power conversion stage. So fundamentally, you've already got a couple of power conversion stages in a charger to go from AC to DC from the grid, and then have a isolated DC-DC converter to the output to the battery charging connection. So wireless charging, there are different ways you can architect it, but basically you have to add at least one other power conversion, which is essentially another isolated DC-DC converter, but with a much larger gap. Whereas the DC-DC converter that isolates the output of a charger through a transformer has a very small gap on the order of like a millimeter or so, depending on how you want to measure it in the transformer. Now, depending on the application, your gap may be a few inches or even a few feet, depending on the size of the vehicle and whether it's on the undercarriage where it's affected by the ride height with the suspension and different weights in the vehicle, or if you're talking about something that's pulling up to or alongside something. So by adding another power conversion stage, you increase complexity and cost and size and losses. There are ways to try to minimize those. There are clever ways to try to build those into the existing architecture of the charger. But at the end of the day, wireless charging is going to fit needs where there are specialized needs that only wireless charging can meet. So in situations where you have to have autonomous or unattended charging, like if you've got a AGV or a AMR, automated robot in a warehouse that needs to come up and drive up to a charging station, then it can charge wirelessly. Although I should say there are still conductive solutions there today that are in use and are actually more efficient and lower cost, which is essentially spring-loaded contacts, plated copper plates that come into contact when you drive up to something. And so if you have autonomous vehicles that have fairly precise driving and these conductive mechanical solutions, have some self alignment features. So, it doesn't have to be super precise. You can still make a connection there and it doesn't need to be wireless. Where the wireless may play more of a role is in a dirty or a corrosive environment where those contacts wouldn't have a good life because they would need a lot of service, wiping, cleaning, replacing the coatings can come off, and there are certainly some applications that are autonomous or there's a high cost of labor and are also in a dirty environment, mining or robot lawnmowers and things like that. So I think wireless gets a lot of excitement because we see it in consumer products, but when you've got a 5-watt phone charger and it takes 10 or 15 watts to charge because it's actually wasting, say, half the energy. That's not a large cost. It's not a lot of extra size. It's not something that a consumer is going to notice versus the convenience and the cool factor of being able to put a phone down on a charge pad. But when you start talking about tens of kilowatts, hundreds of kilowatts, the extra loss, the extra heat and power bill and cost and so on can start to add up. So it's wireless charging, which incidentally tends to use a lot of wire, pretty expensive, finely stranded Litz wire, which is high cost. You'll typically have more wire in a wireless charger than in a wired one. But so I don't want to be totally negative here. Clearly, it is finding applications, and it'll continue to find applications as the technology gets better. But it's going to be one of many solutions. I don't think it's going to replace wired chargers in a lot of applications.
Luca or Erik, any thoughts on wireless charging?
Yeah, I pretty agree with Chris. So I think that the indoor application, for example, as a Zivan, they are the suite. So wireless charging is the suitable solution. But I think that we have also to think about two main disadvantages about this technology. First is that the efficiency is less than the let's call it contact charging. So for example, the fast charging or the onboard charger. And the second, that today there is no standardization on that, on the wireless charging. So for sure, the standardization can help also to reduce what are the current costs. So clearly, there are also a lot of advantages that Chris already mentioned. For example, they eliminated the risk of electric shock, or for example, they increase also the safety of the environment. So for example, we can cite the two main example. One is the Wave. So Wave is the wireless advantage vehicle electrification, that are the bus that move, and during their path, the street, they charge by themselves. So they have to charge through the magnetic induction. Or another example is the magnet that allows to charge the vehicle through the magnetic resonance. So these are the two main examples that we have today. But I think that wireless charging for sure could be also a future trend.
Yeah, I think both Luca and Chris are correct. The only thing I'd add is, there's a bunch of technologies that I think there's a lot of hype around and excitement, but then once you realize there's practical limitations, it's clear that a simpler solution might be better. So remember 5-10 years ago, battery swap was a big thing. People were talking about EVs are all going to have standardized batteries, and you'll go, it's been completely superseded by fast charge. And I think wireless charging is in a similar category, there are specific applications, like Chris said, where it could make sense. But there are so many practical issues with it in terms of efficiency, in terms of losses, even in terms of just alignment of the coils. There's some pretty specific nuances that you have to get just to get it right. That I would say, unless you have a very unique application where exposed contacts, to have conductive charging are not an option for some specific reason, wireless charging, really don't spend too much mind share on it at this time. It's just not. It really is not the right solution for 95% of applications.
We just got one more topic I want to get through before we leave some time for questions, and that's one that it's pretty important to me. I'm big into sustainability, and so battery recycling is something that you see come up a lot in the press, and people trying to recycle batteries, or at least reducing the amount of lithium that we have to pull out of the ground. What are your thoughts on kind of end of life of the batteries, what we do with these cells after they're done, how we define when a cell is done? Maybe we start with Erik on that one, Mr. Cell.
Sure. Yeah, absolutely. So I would say if you're interested in battery recycling, take a good look at Redwood Materials, what J.B. Stafl, the former CTO of Tesla, is doing. I think the key is, there's a variety of different recycling kind of methods and discussions that have been had about, okay, we're going to have people kind of take these second life packs and then use them for different applications and then disassemble them. It's very labor intensive. I don't actually think that's the way to go. What I think Redwood Materials has done is actually scaling up to a very impressive scale, is the ability to basically take a fully completed pack and just throw it into a grinding solution that starts separating out the elemental compounds, that allows us to have a more scalable, lower labor intensive recycling method. And I think that's really what it's going to take. There's a few other companies that are doing interesting things as well. A company that called Electric Goddess has basically come up with this really interesting inert fluid that you can put a battery in that'll like slowly self-discharge the battery, that then can be more safely handled for recycling. So there's some interesting innovation here. I think as we see the materials become more and more of a bottleneck and these recycling technologies scale up, this is going to be more and more common of a thing. And likely what will happen is there'll just be a buyback where the value of the materials is actually somewhat significant. So you might have a end of life, EV battery pack, and a recycler might buy it from you for $200, and they'll take care of it, and then they'll net the benefit on the materials itself. So I actually think recycling looks very promising right now, and it's something that I think some of these larger companies are doing at scale, and I think we'll see a lot more of that in the coming 5 years.
Well, if I would like also to add a few words on this about Erik, that are very, very good words. So we also can say that for the recycling is very important for the battery and so on, but also the reuse of the battery. So for example, if we are thinking on a pretty heavy duty application in which the battery is used every day, for example, for 8 hours per day, what we can do after this period, we can also give the opportunity to this battery to a second life. For example, in some application in which only 1 day per week of work is necessary, and then the third life and whatever also the force. So for example, for that charging, that for that battery that has to work 2 times per year, for example. So this is also an important topic for the recycling, also the reuse of the battery. And clearly, I think that we have also to also increase, to open the mind that we have not only to think about the recycling, about the lithium ion and whatever, all the material, but also we have to design both the battery, but also the charger with sustainable material. So it's a more 360 vision, so not only the recycle, but also the design. And the last point that I also would like to underline, that we have also to consider that we have a double effect improvement from the environment. So for example, we have to think that we can first of all, we can reuse for example, the lithium that we can recycle from the battery, but extract the lithium is a cost. So, and to do it, we need, for example, a fossil fuel. So we need also to think that recycle is important also to reduce the fossil fuel to produce lithium. This is the 2 words that I would like to add.
Yeah, I'd say, I mean, it's a topic which is going to be of increasingly more importance as we move forward. You know, as a society, as we electrify transportation and a lot of these working machines. I mean, we're replacing, you know, fossil fuels which get drilled, come out of the ground, refined, burned, and go into the atmosphere as CO2. We're replacing you know, drilling for fossil fuels with mining for metals and minerals, which also has a huge impact. It uses a lot of fossil fuels in the refining and the transportation and just the, you know, mining of the ore and processing. So closing the loop is important. The lead acid industry is instructive because the, you know, lead acid batteries have a mature for many decades, they've had a mature, typically a domestic or local closed loop, because the batteries are fairly easy to take apart. They're simple from a mechanical point of view. You can separate the lead. It has a low melting temperature. It's fairly easy to smelt and reuse. You can even these days often reuse the acid and even the plastic case. And it's not only easy to recycle, but there is an economic incentive because of the scrap value of the lead, and that's really what, you know, makes it all a success. Some of those ingredients are missing with lithium ion or are trending in the wrong direction. So the economic incentive is the more valuable metals in there, particularly cobalt. So in some of the earlier generations of nickel metal hydride batteries, there's a lot of high value cobalt which could be removed. But much of the work on making lithium ion batteries better and cheaper over the years has been to use less cobalt. So or sometimes even none with chemistries like LFP. So moving forward, the feedstock for the recyclers, there's less and less of the economic incentive. In our battery lab, we get paid by the truck which comes to pick up our spent lead acid batteries, but we have to pay the truck who comes to pick up our spent lithium ion batteries. And I expect that that's going to continue. So, you know, there's a need for policy for, you know, polluter pays or some, you know, built-in fees to make it all work from a economic point of view. And then, you know, the actual processes that are involved, whether it's, you know, pyrolytic with heat, where you're essentially smelting the batteries, you know, grinding them up and smelting them like an ore. You can recover some of the metals like the cobalt, the copper, the nickel, but the you know, the lithium is typically lost in the slag. There are, you know, hydro, like water-based, so acid leaching methods where you can start to recover the lithium as well, but that uses a lot of water, which needs to be treated. You know, it's a difficult challenge, and at the end of the day, what you're recovering is some of the atoms, not the highly engineered materials where a lot of energy and cost went into structuring them in the particular way that they are. But so, getting back to the classic reduce, reuse, recycle, I think the reduce is happening on some levels. They're using less of these materials, and if batteries can be right-sized and made to last longer, then they can be reused as well. But ultimately, the recycling is going to play in there, and this is something that we look at with our battery chargers as well. There's no cobalt in our battery chargers, but up to half the weight is aluminum, and that's a material which can be highly recycled if our chargers are constructed such that they can be easily disassembled. Our work in the past with sustainability with our chargers has largely focused on reduce and reuse. We've made our chargers smaller and lighter so they use less material. They're rugged and reliable so that they will last longer and not need to be replaced, and sometimes outlast the vehicle or the machine that they're in. And we have tools and customer education to let them be reprogrammed and reused. But our future efforts are going to focus on making it easier to reuse and also making it easier to recycle and have more of a recycled content in the chargers that we build.
Okay, just one last quick topic here before we go to questions, and that's on energy efficiency. It's related to what we just discussed, entering a world where resources may be constrained and we don't have unlimited sources of electricity or energy. What's happening in energy efficiency on both the cell and the pack side, and also the charging and the electronic side? Let's see if let's start with Luca this time. Luca, do you have any thoughts on energy efficiency on
Yes,
batteries,
of course, yeah. So for sure, why the efficiency is so important? First of all, because we allow us to improve the battery life. So if you charge, for example, one battery in efficiency, you start to produce heat, so the battery starts to degrade very quickly. So this is one, for example, of the advantages. The second one could be, for example, the reduce of energy consumption. So, for example, you reduce the energy request from the grid, and also this is a topic that I try to explain a little bit earlier. For example, the environmental benefit. We have to think also at the environmental benefits. Why? Because we can produce energy from renewable from renewable technology, but otherwise we produce energy from fossil fuel, so which increase the gas. And okay, then we have also to think about the cost saving, and what is also important is also the reliability that one battery has, also the charger. So these are for me the main topic that we have to think about when we discuss about charging, when we discuss about battery, and we will discuss about efficiency.
Thanks. Chris, any final quick thoughts on energy efficiency?
Yeah, I mean, it's important for the reasons that were listed. I think looking at what's possible, there are diminishing returns with increased energy efficiency just because the system's are already so efficient as compared to internal combustion solutions that might have a theoretical maximum efficiency of 30 or 40%, and in realistic operating is single digits, depending on the usage of the machine. So chargers have a power conversion of efficiency of at least 90%, 90 to 95, depending on whether you're looking at average or peak and what the cables are. Lead acid batteries have a round trip efficiency of 80 to 85%, and lithium is 90 to 95%. So there is still losses there that can be addressed. There's diminishing returns in you can't get to 100% efficiency, and as you approach it, the cost becomes prohibitive. Obviously, with fast charging, when you're generating that much heat from conduction losses, small gains do matter. But the other thing, just to briefly highlight, is that in North America anyway, there's also a regulatory component to this. So there are energy efficiency regulations in California. The California Energy Commission regulates non-consumer products federally in U.S. and in Canada. Battery chargers for consumer products are regulated, which also includes the efficiency of the battery. And actually, the U.S. Department of Energy is currently proposing to tighten those rules, which would have a significant impact both on lead acid, which would struggle to meet the increased system efficiency, and with lithium, where some new rules that would propose to limit the standby AC draw of the charger when it's idle, proportional to battery size, could be a problem for small fast charging lithium. So I think there's some movement here, and if there's any battery makers or OEMs who are listening and want to learn more, you can certainly contact me, as some of these rules are in a state of flux right now. But so I guess just briefly to sum up, I mean, the efficiency matters from a carbon footprint, a total cost of ownership, heat, and life of the battery, but also there's a regulatory aspect depending on the application and the jurisdiction that you're operating in.
Okay, let's close up with our special guest, Erik. Any thoughts on energy efficiency and pack design? And then I got one other Q&A question for you.
Sure, absolutely. Yeah, so I think Chris and Luca covered it pretty well on the charger and conversion side. One note I want to mention that is very important from an energy efficiency standpoint overall over the overall application of the system is phantom draw. So a BMS or battery, it's very important to make sure that you're down in the microamps range when you're actually in sleep or deep sleep or shutdown. And a lot of systems that I've seen and debugged have not had that design feature and are always just sucking a few milliamps. It doesn't sound like a lot, but over 16 hours, 24 hours a week, whatever the period is, that can yield a substantial reduction in net SOC of the battery pack. And so if you actually look at the overall use case for electric vehicle, even phantom draw is not an insignificant portion of that efficiency loss. So I would encourage anyone who's developing a battery system to get proper guidance for the design of the BMS and the system, and feel free to reach out to us as well if you're struggling with that.
Cool, thanks. We just got one quick Q&A here for you, Erik. I'm guessing this is for you. It's from Mr. Clifton Wilby. What's a chemistry that's promising for low temperature operation?
I would say LTO and LFP. There's variants of that are really promising, particularly LTO. It's one of those things where in engineering, everything's all about trade-offs, right? So of course, you're not going to get the chemistry that has the highest energy density, highest charge discharge rates, and is the cheapest and has low temperature performance. But LTO, if you're willing to sacrifice some of your energy density, so instead of 250 watt hours per kilogram at the cell level, you're okay with more like 60, 70, 80, and then also a higher cost per kilowatt hour, you have excellent cycle life and the ability to cycle at rate at very low temperatures. So LTO is an excellent chemistry to look at for that.
Cool, thanks. And that just about brings us to the end of our time. So I want to thank Chris Botting for joining us, and Luca for joining us during most people's dinner time and almost coming up on yours in Italy. And our special guest, Erik Stafl. Thanks again, everyone. Good session.
Thank you.
Thank you too.
Thank you, Conway.
Thank you.
Thank you.
And please join the next sessions from the lobby.